trend analysis. We've heard already a little bit about trend analysis. And we know that we really don't have many records that would provide us data from the 1960s, 70s. So we tend to use the satellite data that are combined from different time periods, right? And we also have ground-based ozone observations that we think are perfect, but we sometimes, have to be careful about that too. So just to give you an update for those of you who have not seen yet the ozone assessment chapter on the past ozone trends, this is the work that Lotus Group, Spark Lotus Group done on combining results from different data sets. So we're not showing you individual data sets, but I mean, this is a consensus between different satellite combined data sets. So you see the pinkish line in in these plots that tells you that the ozone is recovering in the upper stratosphere, which is great. I think I have something that says that. And we have an agreement with models in upper and middle stratosphere. We also, if you look at the envelopes at the bottom, the thin pink lines are envelope of uncertainty for the satellite observations, and the gray envelope is for the models. So you see that there is no really easy way to say if there is a decline or recovery in the low stratospheric ozone. Large uncertainties remain. And then there is still, like we see the differences in the mean trends, right? But we cannot say that they are statistically significantly different. So in the tropics, we agree a little bit more. In the subtropics, we don't agree as well. But we say, okay, well, this is dynamically driven, okay? So that's the work that we will try to address in the next phase of the Lotus analysis. Being a co-chair of the NDAC network, so I cannot really resist not to show you the data. So NDAC has 95 stations, 151 instruments, and they're all very well calibrated. So I'm sure that all of you using the data from the NDAC network to validate satellites. And then we also have a rapid data delivery that Copernicus, for example, is using to validate the ACAMS model. So if you want, you can go to this website. You can look at for yourself if you haven't done it yet. So we have various species. We have total columns. We have vertical profiles. And there are different instrument working group that you can contact to get a little bit more understanding of how these retrievals are done or observed. I work very closely with NOAA. I'm part of NOAA. There is another part of NOAA called DANSDIS that does the satellite operational observations. So OMPS products come out operationally from that department. Jeanette Wild has been my collaborator on many projects. So she's taking the SBUV plus OMPS data. She created the combined data set. Vertically resolved. But what I was asking her to do for this particular one is I want her to match her satellite overpass over stations with the criteria of +-2 degrees latitude, +-20 degree longitude box, and let's see if the zonally average trends differ from the trends of a station, right? So she also does some weighting to get a good daily profile for me, and then she's using the adjustment that she developed for the zonal averages to correct this, overpass data set. Oh, yes. So what we get is, now talking about the ground-based observations. So for years and years and years, I was telling everybody that UMCURE record is self-calibrating activity, but occasionally we change instruments. And guess what happened when you change instrument? You might introduce some step changes because there are some stray light, or some instrumental characteristics that might interfere. They're not large changes, but they sometimes exist. So if you don't account for them, you will see that over Mauna Loa, for example, the trend, that's kind of orangey line, could be significantly different from if you remove those step changes. So that's what we did. We used, worked with some model data sets to help us to identify how much of the step change occurred. We didn't normalize to the entire data set, but we just used some additional help. And so after we've done this, we derived trends from the COH with cohesive data set from NOAA and UMKIR, and so the trends agree much better after we've done some corrections. So on the right side, you will see the plot that came from the Sophie Gadas paper with multiple cutters. That shows you if you take mono-low records, you have UMKIR, microwave, sound, LiDAR, FTIR, and you have 3 readed data sets that comes from Swoosh, SBV, MODIS, MOD data set, and MIGRI-DOP that you already heard this time. So they all pretty much agree with the uncertainties in the tropics. But if you look at the bottom, yes, there is a large variability, and it depends on the sampling, and depends on the natural variability, actually, that comes into play. Why I'm telling all of this? Because we're, trying to focus on if we can improve those trend analysis in the future. So what do? We often do fit, and we're happy, we report the trends, but we can look at the residuals, right? I mean, the model trend that has, solar cycle, QBO, etc. You fit it in the data, and then you start to look at those nitty-gritty residuals, right? Why we do that? Because we could, okay, the top panel is the UMKIR residuals after the trend was fitted. The middle one is satellite. And then I plot the difference between the residuals, right? I go really fancy. And all of a sudden, you start to see there are some differences. And there are some time periods when the satellite and the ground-based do not agree. So the vertical lines in the middle section tells you where the satellite have been added, the new satellite. So you start to look like, oh, well, maybe that wasn't corrected properly. But in this particular case, it seems like it was UMKIR, which is Dobson observation, that might have not been completely corrected. And we know that there was a step change, and a significant step change after the instrument got, destroyed pretty much, we had to replace it. So it's a very good test. We removed all of this large variability. Now we can see all these little details to tell us there is something else going on. So we'll need to look, what's going on. And I removed the volcanic years because they're not interesting. No, actually, we cannot do really well during the volcanic periods. So now I look at the slightly different altitudes. This is upper stratosphere. But look, I mean, this 2005 trend is not looking, I mean, the step change is on UMKIR date does not look like it's been, showing up. However, I left the trend component here. I didn't subtract the trends. So you can see immediately that if I put the trend, the lines that show you the trends, we see that there is a difference between satellite and UMKIR. And if you look at the residuals again, this is pointing to something that's, there is a difference in the way how we treated the data, and maybe it's the COH record. So we're trying to look at that, which is OMPS portion of the record, nadir profile. So we say, okay, let's look at some other records. Do we see similar piece behavior? And for this particular slide, I thought that I will bring you a very nice paper written by a Canadian group on their SAGE OSIRIS OMPS data. And they applied the nonlinear function, the nonlinear trend function, DLM code, which reminds me about losing our colleague, Will Ball, some time ago, but his work is still going strong, people using his methods and data. And we are talking about trends in the low stratosphere because he published that paper. So we are looking at the data that's been analyzed using the DLM. And you can see negative trends, okay, we expected. And there is this maximum like around 2012. So if you think about this, there was a recovery and there was like a stagnation period. Why? Good question. What's causing that? But I'm not using it exactly to talk about the cause of this stagnation or not, but I'm talking about, again, like you have different data sets. Sometimes you do the correction and you start to look at these little nuances, yes, in this data set, and that brings this attention. What exactly you're doing? Did you overcorrected your data? Did you when you homogenize the data? You try not to overcorrect it, so you don't miss important events in the records. So that's another point for discussion. So comparing different trends, different data sets is important. And just because I'm here for the LIM profile group, discussion, so I'm just showing you the work we do with when we take satellite data. So in this particular case, thanks to Natalia, she provided us with overpass data over stations. So this is over Mauna Loa again. So this is climatology 2014-2020, and I'm plotting the difference between version 2.6 and ORMLS, and then on the right side, it's version 2.5 minus ORMLS. So just a summary to see what corrections have been done, that it seems to me that, that the biases still, exist, but they became less stripy. However, the low stratosphere, and that's gonna be a good case for us to go back and look at the version 5 of MLS data to see, because this is version 4 of MLS data, so you can see you're going from the negative biases to the positive biases. So time series, we love time series, right? Because we can look at the different nuances. So this is the difference. At the top of these 3 panels is the monthly mean averages data. So there is UMKIR, there is OMPS LIM profiler, and we mentioned the days of the UMKIR observations to remove these sampling biases. So you see this variability, and the difference is plotted at the bottom. There will be differences because UMKIR is really thick layer. We applied the averaging kernel, smoothed it, but there's still some seasonal variability here and there. But what's important here is that version 2.6 biases are slightly different, but what more important, the drifts. So the version 2.6 relative to the UMKIR have reduced from 0.73% per year to 0.42% per year. MLS, we don't have drift with them. I don't know, it's good. And very small bias. This is upper atmosphere, 2 to 4 hectopascal, 40 to 45. Okay, why not to bring the ozone zones in this picture, right? So the middle panel shows you the ozone zones in layer 4, 32 to 63 hectopascal, 20 to 25 kilometers integrated values. So we can see that, although we know that there is a drop-off in ozone zone over Mauna Loa, but I'm plotting this from 2014, so we removed the bias, but we are looking at the long-term drift. So we have a drift between UMKIR and the zone at about 0.13% per year. So there may be some remaining specific things that still remaining in the ozone zone records. MLS, we compare really well with MLS there. So this is the summary plot. On the left, biases. So you could see that the bias actually have increased, as I showed you, in the lower stratosphere in the version 2.6. On the right side, this is a drift. They are, of course, done pretty crude way. But you can see that the drifts between the UMKIR and the OMPS over Mauna Loa have reduced. And I think that's good. So conclusions, yes, data processing and homogenization are 2 important things we do to get a good idea of what actually we see in our long-term records or combined records. So as I said, LIM profile version 2.6 shows improvements in drifts and biases. However, but still there are some drifts that we would like to investigate a little bit more. Comparing with other data sets, definitely, play with your data. Do not just take the means, look at the long term, look at these little residuals. Maybe they'll tell you some ideas, what's going on with your record. And we do, like to use reanalysis SCCM models to help us with the interpretation of our records. I mean, if you're really lucky, like ACE-FTS, and you have N2O data, CO data to do the trends, look for the dynamical components in your record, great, but if you don't, you still rely on the models to interpret this. And yes, we do continue to do trend analysis, so please join us if you're interested. We have meeting the Friday afternoon. Thank you.